Today we're going to be talking about 10.1 sequences and series. This is part 1 in that series, so pay close attention. The first thing we're going to go over is some definitions so you can understand what we'll be doing this week. A sequence is a list of things, usually numbers, that are in order. There are two buckets that sequences fall under: infinite sequences and finite sequences. Infinite sequences are those sequences that just go on and on and on forever. Finite sequences are a fixed number of terms in that particular sequence. For example, I'm given the sequence 3, 5, 7, 9, ... 3 represents the first term in the sequence, or how we notate it is a sub 1. Sub means subscript. The 1 is written as a small 1, but it's at the bottom as opposed to being an exponent. 5 is the second term in the sequence, or a sub 2. 7 is the third term in the sequence, or a sub 3. 9 is the fourth term in the sequence, or a sub 4. And ... means a sub n. It is the nth term of the sequence. In this written form, this is considered to be infinite sequence because the ... means it continues on and on forever. But if I did not write the ... it will be just 4 numbers in the sequence, which is a finite. So that's the difference between infinite and finite. Sequence notation has a special notation, and we kind of talked about it up there above. It is a sub n, where n, or a sub n, represents the whole term, and n represents the term number. So in this case, n will represent the first number in the sequence, the second number in the sequence, the third number in the sequence, and the fourth number in the sequence. A sub n will represent what that number is. So if my a is 1, if my n is 1, then a sub 1 would be 3. If n is 2, then my a sub 2 would be 5, and so on. Now that we know what a sequence is, we're going to take a moment to look at how to write terms of a sequence. The directions say, for example, number 1, to write the first 4 terms of the sequence is given by a is a sub n equals 3n minus 2. All right, so in order to find the first 4 terms, that means that I'm looking for the first term, the second term, the third term, and the fourth term. So that's okay, so I got A. So I want to find A sub 1, A sub 2, A sub 3, and A sub 4. So all that means is I'm going to take this number that's in the term and plug it in for n in my equation. And then I actually have to solve that part of the equation because that will give me my output, or the term for when x is, or when n is 1. So I'm going to substitute 3 times 1 minus 2 is equal to 3 times 3 is 3. 3 minus 2 is 1. For the second term in the sequence, 3 times 2 minus 2. 3 times 2 is 6. 6 minus 2 is 4. Okay, third term in the sequence, 3 times 3 minus 2. 3 times 3 is 9. 9 minus 2 is 7. Fourth term in the sequence, 3 times 4 minus 2 is equal to 3 times 4 is 12. 12 minus 2 is 10. So the first 4 terms in the sequence is 1, 4, 7, and 10. And all you did was take n, which was 1, 2, 3, 4, and substitute it in the equation where n is. Okay. For B, you're going to do the exact same thing. I want to know what A1 is, the first term in the sequence, the second term in the sequence, the third term in the sequence, and the fourth term in the sequence. So I'm going to substitute everywhere there is an n right behind that equal sign, then that's where I'm going to put the 1, the 2, the 3, and the 4. So first we have to do 3 plus negative 1 raised to the first power. Well, negative 1 raised to the first power is still negative 1, and 3 plus negative 1 is 2. A sub 2, or the second term in the sequence, 3 plus negative 1 raised to the second power. Negative 1 raised to the second power is positive 1, and 3 plus a positive 1 is 4. Third term in the sequence, 3 plus negative 1 raised to the third power. Negative 1 raised to the third power is negative 1, and 3 plus negative 1 is 2. Fourth term in the sequence, 3 plus negative 1 is 4. Negative 1 raised to the fourth power is a positive 1, and 3 plus 1 is 4. So you will notice the first four terms in the sequence is 2, 4, 2, 4. You would imagine that the pattern would continue if you keep going on to the 5th, 6th, 7th sequence. That goes for on this side too. Another thing to note is how the equations is written. A sub n is used when you are writing in recursive formula. Now that really doesn't mean much, but I want you to know there is another way to write this same equation. You may have noticed that you can write it as y equals 3x minus 2. This is called an explicit formula. So the only difference is what letters you are using. When I'm using a sub n and n, then I'm talking about a recursive formula. When I use y and x, then I'm talking about an explicit formula. But they both mean the exact same thing. If I'm talking about the first four terms in the sequence, well, this is the same exact thing. I'm looking for the first four terms in the sequence. The n, in this case, represents your x. 1, 2, 3, and 4 is my x values. And this 1, 4, 7, and 10 are my y values because that's your output after you go through the process. Same thing on the other side. My y is the a sub n, and n represents x. Okay? Now we're going to take a look at example number 2, finding the nth term of a sequence. Write an expression for the apparent nth term, or a sub n, of each sequence. For this example, we are actually going to use the DESMOS calculator. In your Google Slides, you will see a link for using the DESMOS calculator because I have a file that's already filled out there you're going to use for this particular one. This example is just a fancy way of saying what's the equation for the sequence that's given. So I'm given the sequence 1, 3, 5, and 7 and dot, dot, dot. So I'm finding the nth term. 1 is my first term, 3 is my second term, 5 is my third term, 7 is my fourth term, and so on. Another way of seeing the same data is actually writing a table. So 1, 2, 3, 4. Well, how do you know what numbers to write in the X column? Well, I got 4 numbers. So 1, 2, 3, 4, because it's going in sequential order. When X is 1, my Y value is 1. When X is 2, my Y value is 3, because it's the second number in the sequence. When X is 3, or the third number in the sequence, Y is 5. When X is 4, or the fourth number in the sequence, Y is 7. So if we had our TI Inspires, what I would have instructed you to do is make a table in the calculator. And since we don't have our TI calculators, you are actually going to use our handy dandy DESMOS calculator. Okay, so what I have before you now is what your DESMOS calculator looks like. It is a spreadsheet or table that is already filled out for you. So please don't change it. It already works. What you have to do is plug in the values in your table. The table is already set up. Down here at the bottom in cells 2, 3, and 4 are equations that are already will pull in data as you populate the table. So I will show you what that means. So I'm going to put in my table y values 1, 3, 5, 7. If you notice, these 3 cells down here has changed. What it's doing is calculating which equation best fits the data for the table. It is clear that the first set of data is linear because of the straight line. I have 3 different types of equations in here. No, this is not all. This is just all we need to use for right now. The first cell is your linear function. The second one is your quadratic function. The third one is your exponential function, because these are the 3 most common ones that we're going to use in this lesson. Obviously, just by looking at the graph, we know this is linear, so I'm going to use the linear function. Down here where it says parameters, it tells you what data to plug in for which letter. Well, it tells me to plug in 2 for M and a -1 for the B. We all know that linear functions follow the format y equals mx plus b, which is how I have it written up here. Don't change it because this is already set. All right, so when I'm over here on my assignment and it's asking me what the equation is, then you simply need to write y equals 2x minus 1. Okay, y equals 2x minus 1. If you're asking yourselves, well, why come I don't write this in a sub n format? Well, you can. Y is a sub n is equal to 2 times n minus 1. It's just a difference of writing an explicit and writing in recursive formula. It does not matter to me which format you choose, but since your equations are already set up on the DESMOS into y equals format, then I just kept it simple for you. All right, now this was nice and pretty and neat, but let's look at B. I'm going to do the same thing I did for A and make me a table out over here to the side. I got 4 numbers in my sequence, so that means that X is going to be 1, 2, 3, and 4. When X is 1, or the first term in the sequence, is 2. That's my Y value. And -5, and 10, and -17. So now I'm going to go over here to the DESMOS calculator, and I'm going to change the numbers in the Y side. Notice how now the 4 dots on the graph represent what's in the table does not make a clear-cut pattern of what the graph should look like. Okay, in this case, you're going to look at the R squared value. The closer the R squared value is to 1, the better that equation fits to the data. So if I'm looking at the linear graph, my R squared value is only a 0.2. This doesn't fit very well because it's not close to 1. It has to be close to 1. If I'm looking at quadratic, it says 0.5 is better, is halfway mark, but it's still not close to 1. It has to be between, your R values are between 0 and 1. Okay, the closer it gets to 1, the better the data fits that particular equation. But when I look down here at the exponential, my R squared value is a 0.9. So therefore, this equation better fits the data that's being shown. Is it perfect? Absolutely not. It is not perfect by a long shot. That just means that there are other elements in the equation that we're not thinking about. That means it probably falls outside of some normal equation that we usually see, and we just don't have time to go through how to figure all that out. So this just makes it easier for us. All right, down here once again in the parameters section, it tells you what numbers to fill in where. All right, it gave me the A, it gave me C, and it gave me B. That means that Y and X are going to stay the same. It will stay Y and X. And for each letter that's listed down here in the parameters, that's what I'm going to change. So here's what I write on my paper. Y equals, A is -1.45. I'm going to take that out to 2 decimal places. Okay. Times B, which is -1.85. 86 if I'm rounding, raised to the x power, plus C, which is 0.07. Hopefully it didn't get cut off. Y is equal to negative 1.45 times 1.86 to the x power plus 0.07. And if I want to write that using a sub n format or in a recursive formula, then I just change y to a sub n is equal to negative 1.45 times negative 1.86 raised to the x power plus 0.07. Now I actually have the exact equation that this one represents, but like I said, this is just easiest for us to get through the lesson to find out which equation best fits the data. This is the easier way of doing it, and you'll have that link. Factorial notation. Factorial notation is an important sequence in mathematics. It involves terms that are defined with special types of products, and these are called factorials. Okay? The factorial function, which uses the exclamation mark for a symbol, okay, says to multiply all whole numbers from the chosen number down to 1. And we're going to run through some examples. Example number 3. I'm actually going to start with 5 factorial first and work my way up, okay, because I think that's easier. Nope, I'll start with 0 factorial and work my way down. So the definition says to multiply all whole numbers from the chosen number down to 1. It didn't say down to 0. It said down to 1. So what does that mean for 0 factorial? That means that 0 factorial, since I can't be 0, then it must be 1. 0 factorial is equal to 1. That is a standard I need to know thing. You're never going to see 0 as an answer. Okay, 0 factorial is 1. 1 factorial is also 1, because if I'm starting with the chosen number and making my way down, then the only number there is 1. Okay, 2 factorial is 2 times 1. Notice the chosen number is 2, and then I multiply all whole numbers from the chosen number down to 1. So I'm counting backwards, 2, 1, multiplying those numbers. 2 times 1 is equal to 2. Now it seems easy right now, but we're not done. All right, 3 factorial starts with 3, then it's times 2, then it's times 1. 3 times 2 is 6. 6 times 1 is 6. Okay? Hopefully you're following. 4 factorial starts with 4, and then it keeps going. Times 3, times 2, times 1. All right, 4 times 3 is 12. 12 times 2 is 24. 24 times 1 is 24. So let me write this out. So 12 times 2 times 1. 12 times 2 is 24 times 1, and 24 times 1 is 24. Okay? 5 factorial. I'm actually going to show you a shorter way of if you're going to keep doing this. 5 factorial is if I'm counting backwards, I start with 5. Notice that I already did 4 factorial. I know the result of 4 factorial is 24. And if I'm counting backwards, remember 5 factorial is 5 times 4 times 3 times 2 times 1, which 4 times 3 times 2 times 1 is 4 factorial. So really what you're multiplying is 5 times 4 factorial, which is 5 times 24, because 4 factorial is 24, and 5 times 24 is, let's see, that's 0, 5 times 2 is 10, 11, 12. Sometimes I have to, count 2. 120. And the cycle keeps going on and on and on. Okay? So hopefully that gives you some understanding of how to handle factorials. So let's look at example number 4. We're going to write the terms of a sequence using factorials. All right, the directions say to write the first 5 terms of the sequence given by a sub n equals 2 to the n power divided by n factorial. All you got to do is I'm looking for the first 5 terms. So I'm looking for A1, A2, A3, A4. Hopefully I'm giving myself enough space. And A5. All right. So a sub 1 is 2 to the first power divided by 1 factorial. And I thought I should have started with 0. I'm thinking maybe I should have, but it's okay. Okay, we'll just start here. Normally it will say start with 0. Yes, it did. Begin with n is equal to 0. So I'm going to change this. A0, A1, A2, A3, A4. Okay, I'll fix that in a minute. All right, so that's 5 terms. 1, 2, 3, 4, 5. So this should be 2 to the 0 power divided by 0 factorial. Anything raised to the 0 power is 1. 0 factorial is 1, and 1 divided by 1 is 1. Okay? A1 is 2 to the first power divided by 1 factorial. 2 to the first power is 2. 1 factorial, according to my chart up here, is 1. And 2 divided by 1 is 2. Okay? Hopefully we're on the same page here. All right? A sub 2 is 2 to the second power divided by 2 factorial. 2 to the second power is 4. 2 factorial is 2. And 4 divided by 2 is 2. Okay, hopefully we're keeping track. All right, the next one is a sub 3. That's 2 to the third power divided by 3 factorial. 2 to the third power is 8. Divided by 3 factorial, which is 6. Please reduce your fractions, and I can show you how to do that in DESMOS as well. Okay. So I want to use a fraction, 8 divided by 6. Okay, if you click here on the equal, if you click here on this circle, it will change it to a fraction for you. So I typed in 8 divided by 6. I clicked on that circle and it will change it to a fraction for me. It's 4 over 3. And then the last term in the sequence is 2 to the fourth power divided by 4 factorial. 2 to the fourth power, I'm just multiplying another 2 on the 8, so 8 times 2 is 16. Okay, 4 factorial. 4 factorial is 4 times 3 times 2 times 1, which is 24. Reduce your fractions, please. So I'm going to reduce it. 16 divided by 24. Change that to a fraction is 2/3. So the first 5 terms in the sequence is 1, 2, 2, 4 over 3, 2 over 3. If you need to make you a table so that it becomes clear to you what the numbers in the sequence are, then do that out to the side. All right, last example for factorial notation or factorial sequences is to evaluate factorial expressions. And this directions that says write the first 5 terms in the sequence does not belong. So that needs to come out. Okay, so look at A. A is 8 factorial divided by 2 factorial times 6 factorial. All right, so now the definition of factorials once again is you are multiplying whole numbers starting with the number that's given all the way down to 1. So for example, for this example, watch this. 8 factorial is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay, I know I'm going over into that other problem there, so let me try to write this a little bit smaller. Because I'm writing this in pencil because I want you to see something. Let's just write it down here. 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay, divided by 2 factorial is 2 times 1 times 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. Now, instead of running for your calculator and grabbing it, okay, I want you to look at the details here. Notice that 6 times 5 times 4 times 3 times 2 is on top as well as on the bottom. When you have the same number on top divided by the same number on the bottom, then they cancel each other out, okay? That's like saying 2 divided by 2. Well, 2 divided by 2 is 1. So they can cancel each other out. All right. So another way of writing it would have been 8 times 7 times 6 factorial. Because 6 factorial, just like we've written out, is 6 times 5 times 4 times 3 times 2 times 1. Divided by, you would expand out 2 times 1. Times 6 factorial. And now you can see that 6 factorial will cancel out. Okay? 8 times 7 is 56. 56 divided by 2. And 56 divided by 2, if you're not sure, you can always go back to that calculator on DESMOS to type it in there. But 56 divided by 2 is 28. Okay. Okay, so let's look at B. Sorry, just carried over there. All right. B is 2 factorial times 6 factorial divided by 3 factorial times 5 factorial. Well, how you know what's going to cancel out? Well, here's how I know. 2 is smaller than 3, so 3 must include 2 factorial. 6 is bigger than 5. So 6 factorial must include 5 factorial. So I would write this out this way. 2 factorial times, okay, you following? 6 times 5 factorial, okay? Divided by, watch this, 3 times 2 factorial, that takes care of 3 factorial, times 5 factorial. Now, what do you notice? I can cancel out 5 factorial. I can cancel out 2 factorial. What's left on top is 6. It's all multiplication and division, so you can do this. Divided by 3, and that gives me 2. Now, you can put it in the calculator if you want to, but I guarantee you're going to get the same answer. Okay, well, what if I'm not giving any numbers? I'm giving letters. What in the world do I do then? Well, notice the pattern. I would even recognize A. Look at A. 8 factorial was taking 8 and multiply all the subsequent numbers that came before it. Okay? N factorial is doing the same thing. All right? So if 8 went from 8 to 7, how did it get there? It actually subtracted 1. Okay. So first thing I'm going to multiply is N times N minus 1 factorial. Okay? Look what's on the bottom. N minus 1 factorial. Guess what? They cancel each other out. What's left is N. Now that is a concept that you would have to look at, stare at, practice it, understand it. Okay, what's happening in this problem? All right, so you'll know that no matter what I do, this is going to cancel out this. Now, why didn't I expand the bottom? Well, because I got the top to match what was on the bottom. So it was no need to expand the bottom. If I did, it would have been N minus 1 factorial times N minus 1 factorial times N minus 1 minus 1 minus 1 factorial, and it would have kept going and going and going. Okay? My end result would have still been N, no matter what.